Hello. Good morning, students.
Good morning, sir.
Yeah, good morning. The video is clear, right?
Yes, sir.
Okay, thank you. We'll start the class now. Almost, I think everyone would have joined now by 9. Yesterday, we have started seeing about alternating quantity like an AC voltage or AC current, alternating quantity. Okay. So alternating, here we consider a periodic signal which has a period. Over that period, it gets repeated. It has both the positive and negative values, positive and negative values. It has a period. So the period is the time. It may be measured in time or it may be measured in angles also. So sometimes it may be measured in seconds, or it may be in degrees, or it may be in radians. Okay, so it need not be in only. So though we call it as a period, we can be measuring it in degrees also. That we have to understand. Then we have seen like yesterday we have seen cycle. So it is a complete cycle which is getting repeated over the period. And when we know the period, we can find out the frequency of a signal. So these things would have heard at least the meaning of these things. Frequency generally we take it as a reciprocal of the time period. So generally we call it as a time period. As I said, it need not be only in time, it may be in degrees and radius also. So when we want to find the frequency of the signal, just when we know the time period of the signal, we can find out the frequency of the signal. For example, we have an AC signal, which is our electricity board. It may be like our state electricity boards. What is the frequency in India we have? We have 50 Hertz, we all know. Okay. What is Hertz? What is this Hertz? H is that we write it as
Units of frequency, sir.
Yeah, correct. Hertz. Otherwise, we can call it as cycles per second. Okay. Hertz is nothing but cycles per second. What is the meaning of 50 Hertz? It is 50 cycles per second. It means that within a second, for example, our 1 second is here. Let us consider this is 0th second. This is 1 second. So if you have number of signals, if you count this will be number 50 cycles within a second. Or else, if we consider only one cycle is getting repeated. So 50 cycles are repeated in 1 second. If the frequency is 60 Hertz, 60 such sinusoidal signals will get repeated within 1 second. So our generator, our electronic inverter should be designed in such a way that they're able to give an AC signal 50 cycles within a second. So if you want to find out the time period of the signal, what should we do? As we have seen, the frequency is reciprocal of time. Time will be reciprocal of frequency. Okay. So when we take reciprocal of 50 Hertz, what do we get? We get 0.02. It means it is in seconds because we have taken cycles per second, right? So it is 0.02 seconds. It means that to complete one cycle, it takes 0.02 seconds. So for every half cycle, it takes 0.01 seconds. So that is what we infer from the frequency and time period. So as the frequency increases, time period gets reduced. So higher frequency, lower the time period. And then we have seen an average value of an AC quantity, average signal. This one I think I forgot to tell in Nellore students, right? I remembered in Gudur students I have. Okay. So average signal we have seen, and average we have seen like we take only for one half cycle because since it has both the polarities, the values here are positive values, the values here are negative value. You take any instant, we call it as instantaneous voltage or instantaneous current. It means that the value of the voltage of the current, it may be voltage or it may be current, over a period of time, every time it has a value, different value. Okay, so we call it as an instantaneous value of the physical quantity. It may be a voltage or current. So when we take average over a period of time, because of both are equal here, symmetric about x-axis, the value here when we average will be getting cancelled with the average value here. Yesterday we have seen, like by taking 3 values here, we have added and taken the average and taken 3 values here and then added. So 6 points we have taken. When we divide it by 6, we get like 0 value. So it will be average value will always be taken for only one half cycle. Only one half cycle. So generally, what do we do over a period of time? That is, this is over total time period t, but we integrate over only one half cycle. So it is t by 2 integral 0 to t by 2. It may be I of t dt or V of t dt. If you average voltage, it will be V of t dt. Okay. So it will be like a 2 by t integral 0 to t by 2 I of t dt. So for average value. But there is another quantity called RMS value, like root mean square value. Is that clear?
Yes, sir.
Okay. Now, coming to the RMS value, like the full form of RMS is root mean square value, because we face the problem when we take the average value. It is we cannot take it for a period of time. Over a period, it gets 0 value, right? When we average all the positive areas and all the negative areas getting cancelled, so that on average you will get 0. So they found another quantity called RMS value, like the red color is visible. Is it okay? Color? Is it visible? Please.
Yes, sir.
Okay, thank you. Now, okay. Now, I take a value of, say for example, 10 volt DC, 10 volt DC, and I take an of 10 volt AC. Okay. I think it is wet so that it is okay. 10 volt. Okay, right here it is. The duster is wet so that it is.
Sir, excuse me, sir.
Yes, yes. Yes,
Sir,
yes, sir.
sir, myself, G. Venkateshwarlu, HOD, sir.
Yes, sir. Tell me, sir. Good morning.
Some of the students are not mentioned the number, sir, roll number. They are mentioned name. So the attendance is not given for name. Please
Okay,
tell him, sir. Please.
okay, sir, okay.
Oh, okay.
Dear students, you logged in with some other ID, I don't know, the roll numbers are not there, only names are there. So you will not be given the attendance. Students,
Sir,
did you listen to HOD sir's information?
Yes,
Whatever
sir.
he has said?
Yes, sir.
Hello?
Sir.
So please, yeah, please correct it. You will not get attendance otherwise.
Okay, sir.
Okay? Sir?
Okay, sir.
Okay. 10-volt AC. Okay. Now I take a resistor. I take a resistor. I apply this 10-volt DC and I take the same resistor, same value of resistor, and I apply 10-volt AC. Okay. So consider that this is an RMS value, not the peak value of AC signal. Okay, let us consider this as the peak value, not the RMS value. Now, when we apply a voltage to a resistor, what the resistor will do? It will oppose the flow of current. When opposition is there, normally what will happen? There will be heat production, right? Thermal energy will be. Hello? Okay, so the resistor will get heated up for 5 seconds. For example, I apply this voltage for 5 seconds, maybe not 5 seconds, maybe 5 minutes. Okay, and I apply the same 10-volt AC to the same resistor for 5 minutes. AC signal and DC signal. Can anyone tell upon which application the resistor will be heated much? I apply 10-volt AC to the same value of resistor for the same amount of time. Voltage values almost looking the same, resistor value is the same, time is the same. I want to know in which application, either in AC or in DC, the resistor will be heated more.
sir, DC.
Yes, correct. DC will be because it is applied. You see the DC voltage. Sorry. If you see the DC voltage, it is continuously applied. You see, for every instant of time, it is 10. You take zeroth means that first instant, second instant, third, fourth, fifth, any instant you take, the value of the voltage is constant and it is constantly applied to the resistor so that it will be heated up. But when you see an AC signal, this 10 volt, I said it is let us consider it's a peak value. Okay. Normally we mention the peak value only. So it is 10 volt AC. So 10 V sine, like 10 sine omega t or something like that. Okay. Amplitude is 10. So that is the peak value. But the 10 value is not at all the times, right? So it starts from 0, gradually increases, gradually decreases, and then it gets a negative value, and then it reaches the negative peak like -10, and then here it reaches 0, again it gets repeated. So it means that this 10 volt is not the equivalent of this AC 10 volt. So they found another quantity called root mean square value. Root mean square value. When you find this value, that will be having, so you find another x value of AC, you increase the amplitude of AC such that you apply the same amount of, for the same amount of time, you get the same heat as you got in DC application. So this x value is known as DC equivalent of AC. Okay, this x value is what? DC equivalent of AC. DC equivalent of AC. This 10 volt is not equal to this 10 volt because the value looks the same, but you have understood that in the case of AC, the 10 volt peak is not for all the times. It is appearing only for very short time of the time period. So we go on increase the voltage of AC so that we apply that voltage for 5 minutes and you get the same heat. So the work done, what is the work done here? Heating application. So that work done by the 10 volt DC is done by not 10 volt AC, little more than that, because it is not constant all the times. So that value is called as root mean square value. So how did they find that? How did they find that value? Like what they have done, as we have taken the average value, here also they take some number of samples on some instance at different equal intervals. They take the values like I1, I2, I3, I4, I5, I6. Now, when we square a number, the sign becomes positive always, right? Whether we sign a positive number or whether we sign a negative number, the resultant is always positive. So, IRMS, like let us take it as the value of RMS, I, which is equal to, or we write IRMS square is equal to I1 square plus I2 square plus I3 square plus I4 square plus I5 square plus I6 square divided by number of times. Okay. So this is like this they have found. So IRMS is under root. In general, we can write I1 square plus I2 square plus I3 square and so on plus IN square divided by N. So when you square, the value becomes positive, so that it is not getting like average value got 0 value, here it will not get 0 value. So now, though the AC looks as 10 volts, it is not 10 volts. Peak value, you would have seen what is the relation between the peak value and the RMS value, I max and RMS. Do you know that? Have you seen the relation between IRMS and I max?
So we root the IMAX value.
Yeah, root to RMS value. When you multiply the RMS value by root 2, you get the maximum value. So now we have seen IRMS, like let us see the RMS value of current here, IRMS is equal to 10 divided by root 2. So when you want the RMS from maximum value, you divide by root 2, so that it is not 10. Though it looks like 10 like here, DC here, it is not 10 actually. It is divided by 1.4142. 10. So that much value is less. So it does the value of DC voltage, which is equivalent to only this much value, not 10 volt. That is why we get the lesser heater, lesser heating in the case of DC, AC, when we give the same value. So not the same, when you see the amplitude alone, you cannot decide they are the equal values. If it is an AC, if it is a DC, they are different. So you should not consider in the similar fashion. Now, in general, as we have seen, the average value is an integration. This is also a kind of integration. So we see the relation in the form of integration. All these things you would have studied, right? Yes or no? Have you studied these RMS values, maximum values, and relation between them, average value?
Yes, sir.
Okay. So now, IRMS in general, in terms of 1 over T integral I square I of T square dt. So you take number of I1, I2, I3, I4, I5, I6, any number, square them, add them up and divide it by number of times whatever you have taken. So it is like integrating those values over a period of time. Square values are integrated and then added them and then integration and then divided by 2, divided by the time period and take the root. Then it is called as RMS value. Now, after average value, RMS value, these things you must be knowing earlier. After these things, we have a quantity called phase. Coming to another important term which we use generally in the case of AC signals is phase. What do you mean by phase or phase angle or phase? Can anyone tell? Have you heard the term called phase angle, something like that? Yes or no? Yes?
The phase is how many degrees?
Sorry? Yes, tell me.
How many
Sir, it
degrees?
is
How many cycles?
Degrees, sir. Degrees. 360 degrees.
the process of change, sir.
Sorry?
Process of change.
Process of change.
I mean, from one angle to another angle, phase angle.
Yeah, okay. Somewhat related to what somewhat it is related, but let us see about the phase. So when you have a signal like a sinusoidal signal, and we say another signal is there, it is a relative quantity. We cannot say that it is like a relation. If you say someone is short or if you say someone is tall, it is with reference to someone, right? You cannot say just like that. When compared to something, you say this is tall, or when you compare to this one, you can say that this is short. Or if you say someone is faster or someone is slower, it is a relative term. You cannot say you compare with someone and you say he is faster or he is slower. Similarly here, phase also, it is position of the position based on the time or based on the degree, whether it is advanced or it is delayed. So how much it is advanced or how much it is delayed is given by this phase. So it is always a relative quantity. It is not having, when you compare with something, you can say that there is a difference of this. So you take, for example, I draw in the same graph, like when you say this is a voltage, and I'm going to draw another graph, another wave, and it is going to be my current. Okay, this is my current. Now, can anyone tell? Actually, there is a difference of phase. This is what we call it as phase. Okay, so now let us take this as the theta, and this is my angle phi. This is this much angle. There is a difference. It means that the waveform, both the waveforms are not reaching zero values at the same time. They are not reaching their maximum. Their maximum. It may be 5 volt. This may be 3 amps. But 5 volt is the maximum value of voltage. 3 amps is the maximum value of current. Both are reaching their maximum values at different instances. So there is a delay of this. And otherwise, we can say that I can draw another waveform so that you can better understand. So this is my 5 volt and this is my minus 5 volt plus 5 volt, and this is my voltage. Okay, V, and I have current, and this is my 3 amps, 5 volt. Sorry, I have drawn the same. Okay, now you see these 3 amps and this 5 volt are at the same time. They reach 0 at the same time, 0 at the same time, again next 0 also at the same time. The peak value is also at the same time. and the negative peak also at the same time. It means that they are in phase. They are in phase, means they go together. There is no delay or advancement in their travel, in positioning of them. But in the case of this waveform, here you can see my voltage has reached 0 at this instant, but after some delay, it may be angle delay or it may be time delay, you can call it as, my current becomes 0. My current takes a value 0. So after a delay, so voltage has reached 0 here, but the current is reaching 0 at this time only. Similarly, the peak value has been reached at this instant, but my current is reaching its peak value only after some time. So there is a gap between, there is a time delay between. When you measure in time, it is a time delay. When you measure in angle, it is a phase angle delay. Okay. So there is a delay. And it may be an advancement also. My another case may be like this also. In any case, it is called phase only. So you take another thing like now I want to draw the advanced current. Okay, this is my voltage, and I want to advance the current so that I start from here. You can see here I draw like this. Now we can see. You can see here, I consider the peak value at present, okay? At present, I consider the peak value. The current has reached the peak value well before my voltage peak. My current has reached 0 before my voltage has reached. My current has reached negative peak before my voltage has. And my current has reached 0 before my voltage. So the current is advanced. So I'm talking about current only. We can talk about both the things. You can say one thing, that is it may be referred as voltage, or it may be phase angle may be referred with reference to voltage and current also. So when we say here voltage, can anyone tell which one is leading what? I want to see which is leading here in the first graph. This is my first waveform. First one, this is my second one, this is my third one. Can anyone tell? I want to see, I will write here V and I and V like this. So I want to write whether it is leading or lagging here. Voltage leads or lags. Can anyone tell here? You see here voltage is reaching 0 before my current. Voltage is reaching maximum before my current. So voltage leads here. Voltage leads in the first graph. So this is about first. So voltage is advanced here. So before current it reaches. Or if you want to refer in terms of current, current is obviously lagging. When voltage leads, current will always lag. So you say that it is lag. So you can write this or this, both are correct, because voltage is leading current or current is lagging the voltage. So this is in the case of one case. We will see what kind of component will do this. This is a condition, okay? When you apply voltage, what do you do? Generally, you apply most of the electrical sources or current sources or voltage sources. Can anyone tell? We have many electrical sources. No, daily you plug in grinder, mixer, television, mobile charger. What kind of voltage source you give to the source? I mean, you give to the load. All are electrical loads, right? What kind of source you give? Whether you give current or you give voltage.
Sir, voltage, sir.
Yes, all are electrical means voltage sources. Can anyone tell if you come across an current source in your life? Sir, this is a current source. Can you tell anything? Such thing? Because of something, current is generated. Then after it will be dropped as voltage. Generation itself is current. Here we generate voltage and then you connect the load, current flows. But in certain things, there are generation of current, then it gets dropped as voltage. Anything is coming across in your mind? Yes, you all know that device, but you don't know that is doing this job. Maybe or you would have studied also. Okay,
Generator.
sorry,
Generator, sir.
generator. Is that correct? Is that correct? Generator also we get until and otherwise we don't connect a load, there will not be any current flow.
Transformer, sir.
Transformer also voltage only you give. Now you don't think about from your subject what you studied or you're studying now. Just you think okay, let me tell the photovoltaic cell, PV cell, solar cell. Okay, so what does it do? When the photon falls, sunlight falls, there is a valence electron will be jumping from one band to the other band. It gets energized and then it is jumping into the conduction band. So the electrons are flowing there first. Then we take that collection of electrons outside, we connect to the load and we get the output. So this is a kind of current source. But generally there are certain circuits, voltage source can be converted to current source and current source can be converted to voltage source. Okay, leave it. Now this is an example of a particular load, and this is an example of a particular load. Have you come across this kind of waveforms? Like this, like this, like this? Yes?
No, sir.
Have you come across these terms, leading and lagging, in any of
Yes,
the
sir.
subjects? Okay. So perfectly this component, we will see that one in detail, but when you connect an AC source to an inductor, that will do this job, because inductor will not allow the sudden changes in the current. You switch on the voltage to an inductor, it will not immediately allow the current to flow. Gradually it will increase. So there will be a delay. If something is opposing the flow, there will be delay obviously. So the inductor's nature, to give the supply, the current will not flow instantly. Gradually it will get increased. You would have studied in DC transients also, some time constant is there. So it takes some time and reaches the steady state value. So similarly here also, it doesn't flow or it will have the nature of opposing the changes in the current, thereby it delays the current. And what kind of device or what kind of component, all three are within RLC components only. Something is done by R, something is done by L, something is done by C. So L is doing this job. Okay, what job? Delay job. What is delayed? Current is delayed. With which it is delayed? With voltage. So it is reference. With reference to voltage, current is delayed. If you see only current, you cannot say it is leading or lagging. You see voltage, you see current, and you say current is lagging the voltage. Similarly here, there is a device we know, that is resistance. Resistance is having a nature. It doesn't take time. You give voltage, instantly the current flows. There is no delay. Okay, as the voltage goes, current will also go. You give DC, DC current will flow. You give AC, AC current will flow. It means that it follows the voltage as given. But this is not like that. Inductor, you give AC signal, it gets delayed. Current is delayed. It doesn't follow the voltage in the case of inductor. Whereas in the case of resistor, yesterday itself we have seen resistor cannot differentiate whether you give AC or DC. It will do its job. That's all. Always the inductor or resistance will produce heat. When you apply voltage, it will get heated because it is opposing. So the voltage and the current both are in phase. So voltage is 0, current is 0. Voltage maximum, current maximum, voltage reaches 0, current also reaches. Here it is not the case. So that is the case of this. So here, what do we say? We say that voltage in phase with current. Here we say lead. Here we say in phase, or we can say that current also in phase with voltage. Either way, because both are in phase, you can say voltage in phase with current or current is in phase with voltage, both are the same. Okay, in this case, current is leading, you see, the black one is current is advanced, but voltage is falling behind, means voltage is lagging. So in this case, what do we say? VI or IV, what we say?
Voltage
Voltage
lags.
lags or current leads. So you remember one thing, the other automatically. Don't get confused. You remember in the terms of current alone in all the cases, or voltage alone in all the cases. I remember in my, for me, whatever is easier is current is lagging. I remember in terms of current. So in inductor, current lags. In resistor, current is in phase. In capacitor, current is leading. Okay, so I remember only the current in my case. You can remember in any way. So ultimately, you should know the concept. So here, where is the component? The capacitor. Capacitor does this job. That is why in the case of industries, when we have some lagging power factor, you know power factor, right?
Yes, sir.
Yeah. So the delay between these things, when you say the phi of the cost value of this one, you see, you give voltage, current is not flowing at that time. But voltage is getting reduced, but current increases. So if you see the real power which is delivered to the load is not that what you wanted to give to the load, because of leading. See, you have bullock cart, okay? In villages we have bullock cart. You understand what is bullock cart, right? Like
Yes, sir.
in villages we have bullock cart. Both the bullocks, if they pull the load, the vehicle will move properly, right? The load will be properly carried. If one bullock is ahead, the other bullock, or one bullock is behind the other bullock, whether the load will be properly shared and properly taken by the bullocks, no. The same thing is happened in the case of LC loads. When you connect L load, current is lagging. So whatever I wanted to give, that is not delivered. When you connect in the capacitive load, current is leading, voltage is falling behind. Then also my power is not delivered. Real power is not delivered. So the power which is getting wasted, which is not doing any useful job in the case of inductor and capacitor, because of this leading or lagging, we call it as reactive power. What we are doing, most of the industrial loads, you go to any industry, what kind of loads you find? Whether R load or L load or C load, which load you find? Most of the industries or even at homes. Can anyone tell?
Reset RLC.
Sorry?
RLC.
RLC only. See, you take anything, you take resistance. In resistance also, there will be some inductance and capacitance. You take capacitance, there are also some kind of inductive and resistive nature. You take inductance, that will also have some resistance and capacitance. So it is inseparable. They are not separable, but the value dominates these data. For example, you take inductance. Okay, inductance. What do we do? We wind. We take wire and we wound it. Okay, we wind it across some core. But this wire is copper. This wire is copper. Copper will have its own resistance, wire resistance. It may be very small, but it will have some value. Maybe milliohms. Say for example, 1 milliohm. Some resistance, you take any straight wire also. Nothing is 100% zero resistance conductor. Superconductor we don't use now. We use copper or aluminum. Aluminum is having little more resistance than the copper. So it will have some resistance. So what you have done, you wound an inductor. But what it has, some resistance also. So R will be also there in L. And similarly, you wound the wire. This is a conductor. This is a wire, right? And another winding. You wind one wound and another wound. So one wound and another wound, they are the conductors. In between winding, there is some air gap, right? You cannot eliminate the air in between, right? So there will be some gap between these two windings, and these two windings we have some capacity effect. these two windings, we have some capacitance. So you cannot say that there is a 100% pure inductor, 100% pure resistance, 100% pure capacitance. So when you consider a load, it will be mostly, they will all contain R, L, C values also. But the dominating one, L, C. C will be very less, R will be very less, but L will be more because we want a inductor there. So in such case, when you go to any industry, most of the industrial loads are inductive loads. Most of the loads are what? Inductive loads. Because you go to any industry, there will be pumps, there will be motors, like mostly something is rotating, right, in industries. So in such case, what will happen? All the inductive loads, they will make the current flow to lag behind. They will make the current flow to lag behind. So that this kind of nature will be there in all the industries. All the industries, what kind of current will flow? Lagging current. So there will always be a lagging power factor. To take cost value of this 5. Are you there? All of you?
Yes, sir.
Okay. So most of the inductive loads are industrial loads are inductive loads, thereby the current lags. So, but what you wanted? You wanted to deliver the real power what you have, but apparent. What is the difference between apparent power, real power, and active reactive power? Can anyone tell? Yes. What did you have you heard these terms like real, reactive, and apparent? Real, reactive, then apparent. Can you give some example for these things, like what you have understood, like real, reactive, and
యాక్టివ్ పవర్ అంటే మనం కన్జ్యూమ్ చేసుకునే కరెంట్ సార్. యూస్ఫుల్
Sorry?
సార్ అది.
Sorry?
యాక్టివ్ పవర్ అంటే మనం కన్జ్యూమ్ చేసుకోవచ్చు సార్. హౌస్ హోల్డ్స్ కి వాటికి.
Yes. That is the real power which is getting consumed. What is the apparent power? Yeah, you are correct. The real power which is getting consumed only by the load is the real power. That means that is the only power which is doing job. Because you consume, you do your job. You don't consume, you just store. There is no real work is done, right?
Yes, sir.
So that is the reactive power. The power which is given but not doing any job. It is not consumed. It is stored in some form. Why? Because inductor, when you apply something, it will store some amount in the form of magnetic field. Okay, it will store some value in the form of magnetic field. And when you apply a voltage to a capacitor, it will also store in the form of electrical field. Okay, it will act as a battery, plus minus. Real job is not done by these things. The energy is stored in these things. But here you apply voltage, immediately it will get heated. So the job is done by inductive reactive components. Real power is consumed by only the resistive part of that, and the other parts they just store energy and then they circulate the energy, and real work is not done by them. So reactive power is the power which is being, it may be called as consumption of the power by the inductive and capacitive components. And what is this apparent then? What is this apparent? Sorry?
Both real and real.
Yeah, addition of these two, real and reactive power, we call it as like apparent power. And have you ever seen transformers are always rated as kVA, correct? We give the capacity of the transformer in terms of kVA. Why? Because we don't know the load. You purchase some transformer from the market, like for example, you are working in an electricity board, you purchase a transformer, but the load, there are thousands of houses. One house differs from the other house load. One house may be an inductive load, more inductive load, another load may be more capacity. Capacity loads are less, but the inductive values may differ. You don't know the power factor. You don't know how much inductive their load is. So you don't know the other side of the load, whether they are unity power factor load or lagging power factor load or leading power factor load, so that you mention them in kVA. So here apparent power is always mentioned in kVA. What is the unit you use for reactive power? kVAR. You have seen these things, right? Yes or no?
Yes, sir. KW, MW.
No?
Yes, sir.
Yes. Now I will give an example for this, so that then we will move on to the actual thing. Okay. Now you have a water tank, and you borrow water tank of 1000 liters. Okay, 1000 liters, and there is a pipeline which is connected to the tank. Okay, you have water scarcity. You have to buy water 1000 liters. Okay, for example. So there is a lorry comes with a tanker. Okay, so tanker lorry comes, like I don't draw that properly. Okay, so tanker lorry, this is having 1000 liters. Okay, and your tank capacity is also 1000. You bought 1000 liter, but there is some this pipe is not a uniform pipe. Say for example, there is a little bit gap here, like gap, not in the gap, it is like a storage. So what do you do? You connect the pipe here, you let the water to flow inside. The tank was empty earlier, there was no water in the tank at all. After you all emptied the tank, and you found only 900 liters in this tank. Okay, now where that 100 has gone, 100 liters has gone here. 100 liters. Sorry, is that okay?
Yes, sir.
Okay, so now this is your apparent power. You bought a generator or you bought a water tank. This is an apparently, it means that it is imaginary power. They call it as imaginary power, apparent power. So you think that you bought 1000 liter, you will get 1000 liter. You bought the lorry with 1000 liter water, but when you fill your tank, you got only 900 liters. So the apparent power was 1000 liters, but real power is only 900 liters, where that was given, that was stored. That is stored, that is not used. You cannot use this one. Okay, just it cannot be like that. When you get a generator of 1 kVA and you connect it to a 1 kVA generator you bought, you connect a load of 1 kilowatt, but it is of 0.85 power factor, 0.85 power factor. So when you connect, you can load up to 800 watt. You go to 850 watt. Okay, but when you connect 900 watt, it cannot deliver. Why? Because the real power which can be delivered by this load is only 850. Though your generator is 1000 watt, 1000 VA. This is what? 1000 VA. If you connect a load of 0.85 lagging power factor, so only 850 watt load it can take. So apparently it means that it can load up to 1000 watt unity power factor, but you can load the generator only 850 watt. when you try to load more than 850 watt, what it will do, it will switch off because of overload. You think, this generator is capable of delivering 1000 watt. I connected only 850 watt. Why it is not delivering it? It is getting switched off because of this. Because that 150 watt is consumed by the reactive component of your load. So real power can be only 8. So this is the difference between real, apparent. So when you get a generator from the market, you should not think just like that you calculate the load. You have to consider the power factor also. So by considering the power factor, you have to go for additional. Your load is 1 kilowatt, but 0.85 power factor. You have to overrate the generator. Maybe you may go for 1.5 kVA generator so that you can load up to 1000 also. So please think of these things. Okay. Okay, so just we have seen that there is a lagging, leading, and in phase. These are the things we have to think about when you think of RLC components. Just a minute. Okay. Now we'll go for the circuit in which the phase leading, lagging, how much it will be leading, how much it will be lagging. These things you have studied in any subject. Have you studied what will be the angle which is led by the current in capacitance or lagged by the inductor, current in the inductor? Yes or no? Hello? Are you there? Students? So if you don't answer, I think there is some problem in the network.
No, sir. We are hearing. No
Oh,
problem.
okay.
You can continue.
Yes, sir. Yes, sir. Sorry, I thought.
No.
Nobody
We
is
are hearing, sir. Everything is correct.
Something problem in the.
No.
Okay.
No.
Now we'll go for like RLC networks. Okay, so that in the case of when we excite an OR network or OR circuit only with an AC signal, what happens? Okay, so OR load. So OR load with AC. With AC. OR load with AC. So just to take an circuit like just connect it to an resistive load. Let us assume that there is a current of I of t, and okay, and B sin omega t or B t. Okay, so let us take like this. This is R, and let us consider like I, that is I of t. The current which is flown here is Im sin omega t. Here we take it as Vm sin omega. So the applied voltage is Vm sin omega t. The current is Im sin omega t. Now we all know that what is the voltage across the resistance is given by IR. That is I of t. For simplicity, I omit this of t. All are function of time only. So here we have IR, that is R into Im sin omega t. So it is simply, there is no phase angle difference, as the current is a sinusoidal signal which is not having any phase delay between the voltage. So my voltage across the resistance is also the same in phase. So that is what we have already seen. When you have applied a sinusoidal input, the current also follows the voltage. the same sinusoid. It means that when you substitute 0 here, that is omega t is 0, the entire value will become 0. When you substitute here 90 degrees, it will get the maximum because sine 90 is 1. So you get Im r. When you apply 0 again, it will get 0. When you apply this 270, that is this time you will get negative value because sine 270 is -1. And then sine 360 is 0 again. So you will get like that. So my voltage and current, they are in phase. That is what we get mathematically. Whatever we have seen earlier, we mathematically see here. Similarly, when you apply an L load with an AC signal, you consider the same. Just you take the inductance alone. So VM, sorry, here you take it as capital V because it is peak value or maximum value, VM sin omega t. Current flows here, I of t, L. Okay. Now, have you, what is the value of, okay, this is actually V of t. Instantaneous value, okay? V of t. What is the expression of the inductive voltage drop? What will be the value of the voltage which is getting dropped in this is you would have come across L di by dt. Correct? L di by dt. Now, L into what is I here? It is cos omega t, right? So L omega Im. L omega Im cos omega t. Okay. So differentiation of this one. I just differentiated this one. So what is L omega? It is the reactive, that is inductive reactance. We can write it as XL. And then Im cos omega t. Okay. And then this can be rewritten as XL Im sin omega t. Okay.
Sorry to sir, there is no visibility, sir, while you are writing, sir.
Okay, sorry. From here or here?
Sir, here, yes, sir, there, sir. Yes, sir, yes, sir.
Okay, just a minute. Okay. So I replace this one with inductance. So I want to know what happens to the inductive voltage, the voltage across the inductance when I apply a sinusoidal input. So I know that the voltage across an inductance is given by derivative, the L times the derivative of the current which is given. So that this is the one which delays the current. Okay, doesn't allow the current to flow instantaneously. It takes the derivative of it. So L into, when you differentiate this one, you get Im cos omega t to omega. With respect to time, when we differentiate, you get omega here. So it is omega L I take this omega L and then Im cos omega t is equal to omega. We can write this as the reactive inductive reactance XL Im sin omega t. I can write sin omega cos omega t in terms of 90 sin omega t minus 90. When you apply the trigonometric of this, you get cos. Okay, this is cos and sine relation. So what does it indicate? It means that my current is, sorry, this is inductive, right? Cos is omega t, I think, plus here, because the voltage of t, VL of t, sin omega t plus 90 will be my cos omega t. So what you have to do, you to draw the cos omega t, what you have to do, you have to take the sine and add 90 with that. So how do we draw? You take sine. This is my sine. Okay. What is this one? This is my current. Why it is my current? I take this as Im sin omega t. Im sin omega t. Now, what do I get? The voltage. Voltage is not sine, it is cos. You see, in this case, VL of t, it is not sine, it is cos. So, but I take the reference of sine. What is the relation between sine and cos? Cos will be 90 degree ahead of sine. Okay, 90 degree ahead. So, I draw the cosine waveform here like this. So, I add 90, I take 0, I add 90, I take at that instant. Okay, I shift the waveform 90 degree ahead, so that I get like this. I get like this. So what is this one? This is my voltage VL of t. Why? Because I added 90 with that, it becomes a cosine wave. Now, from this, mathematically I have found that the voltage is leading or current is lagging. Just we have seen in the earlier thing, like V leads I, or I lags V. This is why we call it as leading or lagging. By mathematically we have to see. So this happens in the case of inductance. Now, is that clear?
Sir.
Yes.
Yes, sir.
Okay, thank you. So now I replace this one with capacitance, and then just a minute. Okay, I replace this with capacitance. Okay. Okay, same voltage is taken, voltage source is taken, and it is given to a capacitance. What is the voltage across the capacitance? 1 by C integral
IDT.
I of IDT, correct. So you take the integral Im sin omega t. So this will be minus cos omega t, right? When we integrate, so minus Im I take out, by C is there, cos omega t. With respect to dt we integrate, so by omega will be there. So that this is equal to minus Im by omega c cos omega. Okay. So this is minus cos omega t, right? It is not, earlier we got plus cos omega t, here it is minus cos omega t. Earlier we got, by adding 90, you got cos omega t with sine. Now you have to subtract 90 to get that one. So that what you get, Im by omega c, that is sine omega t. This is minus 90. So here, what do you get from here? You get, it is not following the same current. It is sine omega t. It is not sine omega t. It is, sorry, it is the voltage, full voltage, right? So don't take like that. The voltage is not having the same sinusoidal thing. It is delayed with the reference. That is the reference we have taken current here. So the voltage is lagging. This is what? Sorry, again the here you cannot see here, right? Okay, I write here. Can you see this portion?
Yes, sir.
Okay. So I write like Im by 1 by omega c can be written as what? What is 1 by omega c? Xc, yes. So Xc, that is the capacitive reactance, and then minus cos omega t, I can write like the sin omega t minus 90. Okay, so when you have a reference current, here this is reference current, that is, I take the current as the reference, sin omega t. My what happens to my voltage? Vc of t. Vc of t is lagging behind the current. So this is my 0 of my current. I lag 90 degree. This is my 90 degrees because this is my pi by 2. I start from here to draw the current, sorry, voltage. I start earlier, what did I do? I started from here. Okay, in the case of inductance, because the voltage leads there, but here voltage lags. So I lag behind the current. So mathematically and graphically, we have seen that capacity, in the case of capacitance, the current leads the voltage, like or voltage lags. V lags current or I leads voltage. So mathematically also we have seen that. Is that okay? Is that okay? Okay. So with this knowledge, we go to the actual topic, like we go and connect. See, as I said, there is no pure inductive, there is no pure capacitive, there is no pure resistive load. So there will be combination of all these three, but something will be dominating the other, then we call it as that particular load. As I told, most of the industrial loads are inductive loads. If someone is behind you, there should be someone to pull that person close to you so that you both go together, right? In the case of bullock cart, one bullock is ahead, another bullock is behind. So if someone is pushing this bullock in the same place, like the other bullock, then they can both go together, they can take the load together so that the full capacity of the bullocks can be utilized properly. So similarly, if someone is lagging, you know that someone can lead also. What that, if your inductance is lagging, what can lead the current? Capacitance. So the loads are inductive loads, but intentionally, purposefully to add capacitance so that how much is current is lagging behind, because of the addition of the capacitance, you lead that current, how much it is lagging, then you will make them to go together, that voltage and current to go together, so that the real power will be your apparent power. There is no reactive power, because it is getting compensated. That what we call as reactive power compensation by adding capacitive bands. All loads are inductance. No load, mostly no loads are capacitance. Very rarely loads are capacitive in nature. They may be resistive, like heating loads. All heating loads may be resistive loads. All other motor loads, pumps are there. They are major loads. You go to lighting loads are very small loads, right? Industries, maybe huge pumps to be there, 10 HP pumps, 20 HP pumps. So they are very huge loads. When you consider them, these capacity loads are very small. So you add intentionally that kind of a panel. When you go to a power plant or any control room, you can see a panel called power factor correction panel. So you open that, you see only capacitance. So they add capacitance as loads so that they lead the current, thereby it makes the power factor to be unity. Okay. Is that okay? Yes? Students? Okay. Are you following, or am I going fast, or is it okay, or I should go slower?
Sir, no, sir. No, sir. It's good,
Is
sir.
that okay?
Yes, sir. Yes, sir. Okay, sir.
Okay, thank you. Okay, now what we are going to see, very first topic given in the third module is like sinusoidal response of an RL circuit. So response means, as we have seen in the last class, there will be steady state response and transient response. So when you apply a sinusoidal input to an RL network, so we have seen how R will behave. Sorry? We have seen how R will behave. We have seen how L will behave. R will be having both the voltage and currents in phase. L will have current to be lagging behind the voltage, that we have seen. So when we combine the load like R and L, how they will behave, like that we are going to see. So here, let us take the circuit like this, and you have a switch there, and resistance and inductance. Okay. So let us take like V cos omega t plus theta. And this is my switch. Like this can be taken as sine or cos with some phase, okay. It may be 0, it may be any value. Just you consider a standard thing in which you have cosine or sine. Some books they take sine, some books they take cos. The book, the textbook which is given Sudhakar and Sudhakar book, they have taken cos, so I follow that one. Okay. Some book you refer sine, both are correct only. So don't worry about that. Just we need to find. Then when you close the switch, there will be a current flow of I of t, R and L. Okay. For simplicity, when we write, we omit this T. Okay, we write only I. Okay. So now, when we close the switch, the current flows, and we can apply which Kirchhoff's law? K.
KVL, sir, KVL.
Yes. So when we apply KVL, what do we get? The current through the resistance is the same as the current through the inductance. Why the currents are same here? Why the same current is flown to both L and R? Because they are in series, right? You know series and parallel combination. These are connected in series, right?
Yes, sir.
Yeah. So the same current will flow. So we get a drop here. We call it as IR drop. We get a drop here. We call it as inductive voltage, that is LdI by dt. So when we write that one, the drop across resistance IR, this is the drop. So sum of the applied voltage, the potential rise is equal to the sum of the potential drops as per the KVL, right? Whatever you rise, they all should be dropped. So rise should be the drop. So this is the potential rise. You apply voltage. Voltage is a rise. They are getting dropped across these things. You add these two, you will get this. So the drop across resistance is IR plus the drop across the inductance. The drop across the inductance is L di by dt. So these are the drops. And my KVL says, not that KVL says, it is there, but it is said by Kirchhoff's. But it is the natural thing. So whatever the rise, that should be dropped. So V cos omega t plus theta. So this is as per the KVL. We apply KVL. Just we close the switch, we apply the KVL. Now, what do? We divide the entire thing by L. Okay, we divide this by L. So that what we get, I R by L plus L by L will get cancelled. So what do? I divide by L throughout. So di by dt is equal to V by L cos omega t plus theta. And then I rewrite this one in a form like I take d by dt plus R by L into I is equal to, that is, it is a first order differential equation. So we are going to find out the solution of this one. And from the solution, we can find how a sinusoidal input to an RL component, RL circuit will behave. Transient part and steady state part, we will find them out. Omega t plus theta. Okay, so this is the differential equation. We need to find out the solution for this. When we find the solution, we can say how the circuit will behave. Now this can be written as d plus R by L I V by L cos omega t plus theta. Now let us let us take the solution of this one, the complete solution. I of t will be, it will take the transient part and steady state part. Okay, transient part we call it as complementary function, and the steady state part we call as particular integral. Okay, so if we will be having this I of t, which will have a transient part plus some steady state part. So now let us find first the steady state part, then we will move on to the transient part. If you want to copy, or shall I wait for copying or shall I proceed?
Copy it, sir.
Copy, okay. So I erase this and I start from, the board is visible from here? From the top?
Some down, sir.
Huh?
Sir, some down.
The sinusoidal, from here it is.
Okay,
visible.
sir.
Okay. So we need to find out the IP here. That is the steady state part of the circuit, the current part. Let IP is equal to A cos omega t plus theta plus B sin omega t plus theta. See, when we apply the voltage may be having a cosine form, okay? But when you see the current, it may take a combination of sine and cosine, okay, sometimes. So we take the standard form of the current, that is the steady state, it will take both the part. So we are going to find out how much the cosine part and how much is the sine part by finding out A. So just you take, let IP is equal to A cos omega t plus B sin omega t plus theta. Now what do I want? I want the derivative of current, right? We have seen d by dt. So I take the derivative of that one. That is, I take, I differentiate this, okay? So when we differentiate this, what do we get? Minus A omega sin omega t plus theta. Correct? Sorry. Is this correct? We differentiate this, differentiate with respect to time, okay, not omega t, with respect to t only, so that we get here cos into, when we differentiate cos, we get minus sign, and then plus b omega sin omega t plus, sorry, cos omega t plus theta. So this is my I, that is the d by dt, di by dt. So I know we have seen that it is IR into LDI by dt, correct? So I substitute that. So what do I have? I have IR plus LDI by dt is equal to V cos omega t. Since I don't have that one, I am writing this. Okay, you need not write. So now I need to substitute this I. This is my this is my I. This is my derivative of I. So both the things I substitute. So instead of I substitute this IP, and instead of this di by dt, I substitute this. Okay. So what do I get? A cos omega t plus theta plus B sin omega t plus theta. What is this? This is simply R. I need to multiply with R because it is IR plus L into derivative of this one, that is minus A omega sin omega t plus theta plus B omega cos omega t plus theta. So what did we complete? We complete only this portion. We substituted this and this. and then this should be equated to what? B cos omega t theta. B cos omega t plus theta. Now we compare the coefficients of sin omega t and cos omega t plus theta on either sides. What do we do? Comparing the coefficients of sin omega t plus theta and cos omega t plus theta, we get. So I take first the cos. This is my cos omega t plus theta. And where else I have cos omega t plus theta here, and I have cos omega t plus theta here. So on either sides, I am comparing and equating them. So here, what is the coefficient of cos omega t plus theta? It is simply A. So A. And what is the coefficient of cos omega t plus theta here? It is B omega L plus B omega L. B omega L, because here B omega L, L is common for this and this, so I take this, which is equal to, here what is the coefficient of cos omega t plus theta? V, simply V. So it is A plus B omega L. On comparing first with cos omega t. On comparing the sin omega t terms, I get B here. Okay, I get B here, and then minus A
Doubt, sir.
omega L,
Sir,
which is equal to 0 here, correct? What is the sign term here? Are you there?
sir, we ought to write a AR, sir. There is a coefficient R, sir. AR.
Oh, sorry. Yes. R is common with this. Yes. So R. Thank you. So this R is common with this, L is common with this. So we consider this with this and here. Okay. And here there is no coefficient of sign. Sorry, there is no term of sign here. So we get like this. Now, let us take this as first equation and this as second equation. We need to solve this to find A and B. Okay, there are these two equations. We need to solve this one. Okay, now B by R. Okay, let us find out. So now I rewrite this one like I write second equation or first equation I write B omega L. First equation I write. First equation is rewritten like this: B omega L first, and then plus RA is equal to B. Let us take this as first itself. Then I need to multiply and divide by second equation. Second equation is multiplied with omega L and divided by R. Second equation, I multiply by omega L and divide it by R, so that I get B omega L minus A by R omega L square is equal to 0. Because I take the second equation and I multiply by omega L and divide it by R. I don't want this R, I want omega L. What I want omega L, I multiply. What I don't want, I divide it, so that I get B omega L here, and then omega L is already there, so that omega L square by R. So now what do? We subtract these two equations. let us take this as third equation.
No, sir,
Sorry.
there is no possibility, sir.
Yeah, just I write here. So 1 minus 3, what do we get? The equation 1 and the equation 3. These two will get cancelled. Then what do we get? R A is common. So take A common here. Then R plus omega L square by R. Omega L square whole square by R, which is equal to V minus 0 is B. So what is my A? A is B divided by R plus omega L square by R. Or I can take this as the other way, like I take R out here. Okay, or I divide by, actually I multiply and divide by R into R plus omega L the whole square by R. Okay. So that, are you able to see this question?
No,
Yes.
sir. No, sir.
No. Yes or no?
No, sir.
Is this visible or not?
Sir, a little much, sir.
Sorry?
Sir, a little much, not as clear, sir. It is-
Oh,
Sir,
because of the color or what?
sir, up to A equal to V by R plus WL whole square by R is visible, sir.
This one is okay. This question is not visible for you.
Sir,
Okay.
it is no clarity, sir. No clarity.
Okay. Is this okay?
Yes, sir.
Okay. I write here, okay? This question is clear, right, for you?
Yes, sir.
So what do? I take A here, which is equal to B divided by R plus omega L the square by R. I multiply and divide by R. So VR by R into R plus omega L the square by R, which is equal to VR by, when you take R inside, you get R square. When you take this R inside, R will get cancelled. So R omega L square. So this is your A. What is A? Is this one. That is VR divided by R square plus omega L the whole square. Similarly, we need to find B. By substituting A, we can find B. Shall I erase this?
Yes,
Shall I
sir.
clean? So you got A and now we are going to find out B. So substitute in A of these equations. I think it is easier to substitute here, so that I substitute here. Substituting A in 2. Equation 2, what do I get? R B minus A. What is A? It is VR divided by R square plus omega L the whole square. That is my A into omega L, which is equal to 0. Now I want B. Before that, I divide the entire equation by R. Divide by R will give me B minus R will get cancelled, so that I get B only. This R and the division R, dividing R will be getting cancelled. Omega L square, omega L equal to 0. Then if you take that the other side, it will be V times omega L divided by r square plus omega L the whole square. So remember in A, in numerator you have r. In B, in numerator you have omega L. Just to check cross checking, okay, whether your A and B values are correct. Denominator will be Z value, total impedance. Other square of that one, r square plus omega L. If this is okay, you can proceed. If you don't get A and B like this, in A you have r in the numerator, in B you have omega L in the numerator, then you can proceed with these values. Otherwise, you have to check and then you correct it. And denominator is what? Z square. Z square is what? Z is impedance. Impedance is the resistance square plus the reactance square, right? Omega L square. Here only an inductance is there, so only inductive. That is what is here. Okay, so denominator you can use it as the value. You can check whether it is the impedance value or not. Okay, so just we have found the A value and B value. We are going to substitute them in IP. Shall I erase this?
Yes, sir.
Okay, thank you. What is the time now? Okay, we have 5 minutes more. Okay. So A and B values we have found. So we have got the value of P, that is the A cos omega t plus B sin omega t we have seen. So A cos omega t. So you write A value VR divided by R square plus omega L the whole square cos omega t plus theta. This is the first part, that is, then B part is B omega L divided by R square plus omega L the whole square sin omega t plus theta. So this is with B. Okay, so we have found IP, and the transient part IC, we have seen the total solution of the current will have the transient part and the steady state part. This is the steady state part we have found. Then we add with the transient part. Or else, just a minute. We have to find out the magnitude and the phase angle form. We are going to represent this. Let us take the coefficient of cos omega t as m cos phi. Let m is equal to, m cos phi is equal to VR divided by R square plus omega L the whole square, and m sin phi is equal to V omega L divided by R square plus omega L the whole square. Now, when you find squaring on both sides and adding them up, you get m square cos square phi plus m square sin square phi. What do? We square and then add with the square of this, which is equal to
2m square.
Sorry, not 2m.
So sorry, sir. M square.
M square only. We square and add. Okay, squaring and adding on both sides. Squaring and adding. Okay, you just see here. You will not get confused. So it is, we square this one, and then we square this one, add them up. So you square this. What do you get? VR the whole square divided by R square plus omega L square and its square. Okay, you see, this is having a square term and it is being squared here like this. Plus V omega L, the square, divided, denominator will be the same, R square plus omega L, the square and its square. Okay. Now we take m square, which is common here. We get cos square phi plus sin square phi. We know that sin square theta and cos square theta is 1, correct? This will be 1. Equal to, we take the common as, I think this portion I write here. I write here, same thing I repeat, you copy from here, it is m square cos square phi plus sin square phi, which is equal to, I take the denominator as common, that is R square plus omega L the whole square, its square, because we square the terms. Numerator we get V R the whole square plus V omega L the whole square. So we know that this is having a value 1, so that we have on left m square only. Here we take V square common, so inside we get R square plus omega L the whole square we get. We take V square common, you get R square and omega L square in addition, divided by R square plus omega L the whole square and its square. So one term will get cancelled with the denominator. So we get m square, or m is equal to b divided by square root of R square plus omega L the whole square. So what is this one? This is the magnitude of the steady state part. M means magnitude. Okay, magnitude of the steady state part we have got. And will, is that clear? Yes, up to this. Hello.
Sir,
Yes, sir.
Okay, thank you. So we have not completed. We will complete this and we'll solve your problem in tomorrow's class, or if we get any other class today also, we'll see that one. So with this, this is the pure mathematics, right? It's not. If you see this one, you can refer books also. You can easily follow. If you have any doubt, you can ask me. We'll continue in the next class. Thank you so much.